All right, welcome. In calculus, a super common problem is finding the absolute highest or lowest point of a function. But there's a catch. You're usually only looking within a specific window. It's kind of like finding the highest peak on a hiking trail, but only caring about the section between mile marker 1 and mile marker 5. So today, we're going to master the one foolproof method for doing exactly that.
So let's get right into it. Think of this as a hunt. We're hunting for what we call absolute extrema. And that's just a fancy term for the single highest value, the absolute maximum, and the single lowest value, the absolute minimum, of a function on a closed or bounded interval. So here's the big question, right? We know these points have to exist, but where are they hiding? I mean, where do you even begin to look? Is there some kind of shortcut, a treasure map maybe, to find these hidden values without checking every single point? And the answer, thankfully, is a huge yes. And this right here is our treasure map. It's awesome. The absolute highest or lowest points can only be hiding in one of two places. Think about it. They're either at the smooth peaks and valleys where the graph flattens out, where the slope is 0. We call those critical points. Or they're right at the edges of our interval, the endpoints.
And that's it.
Why? Well, because for a point to be the absolute highest or lowest, the function has to either be changing direction, like going from up to down, or it has to be at the very boundary where we stop looking. So just like that, we've taken an infinite number of possibilities and narrowed it down to just a handful of suspects. So this treasure map of ours, it has an official name. It's called the closed interval method. And let me be clear, this isn't guesswork. It's a systematic, step-by-step procedure that guarantees we will find the absolute max and min every single time, as long as our function is continuous, of course. Now, you might be wondering, how can we be so confident? Well, it's because we've got some serious backup. It's this powerhouse of a theorem called the extreme value theorem. This theorem is basically our written guarantee. It promises us that what we're looking for actually exists on that closed interval. So our hunt is never going to be a wild goose chase. There is an absolute max and an absolute min, and our method is designed to find them. Okay, so here it is, the 3-step process. It's so simple, you're going to love it. Step 1, find your critical points. That's just where the derivative, f prime of x, is either 0 or undefined. Got it? Okay. Step 2, evaluate all your candidates. Who are the candidates? Well, it's the critical points you just found, plus the 2 endpoints of your interval. You take all those x values and plug them back into the original function, f of x. And finally, step 3, you just compare the y values you got. The biggest number is your absolute max, the smallest is your absolute min. That's the whole game. All right, theory is one thing, but let's actually see this method work its magic. We're going to walk through a classic example together, step by step. You'll see just how clean and powerful this really is. Okay, here's our function for this round. F of x equals 3x to the 4th minus 4x cubed. A nice, straightforward polynomial. And we're locking it down on the interval from -1 to 2. So our mission is to find the absolute highest and lowest y values this function hits inside that specific window. All right, step 1, we need to find those potential peaks and valleys, right? So first thing we do is take the derivative, a little power rule action here, and boom, the derivative of our function is 12x cubed minus 12x squared. Remember, this new function tells us the slope of our original curve at any given point. Okay, so now we want to find where the slope is 0. Easy enough. We just set that derivative equal to 0. Looking at this, we can factor out a 12x squared, right? That leaves us with x minus 1 in the parentheses. And that gives us 2 spots where this thing is 0, at x equals 0 and at x equals 1. Now, super important check. Are both of these points inside our interval of -1 to 2? Yep, they are. So they're both valid critical points we need to test. And now for step 2, we have to evaluate our list of suspects. So what's on the list? We've got our endpoints, -1 and 2, and we've got our critical points, 0 and 1. So that's 4 total candidates. We take each one of these x values and plug them back into the original function. What do we get? We get 4 numbers, 7, 0, -1, and 16. And now for the easiest step of all, step 3. We just look at our list of results and compare. What's the biggest number there? It's 16, no contest. So that's it. That's our absolute maximum. And notice where it happened, at the end point, x equals 2. And what about the smallest value? That being -1. So there's our absolute minimum, and this one was found at the critical point, x equals 1. See? This is a perfect example of how the answer can be hiding in either place. We had one at an endpoint and one at a critical point. You have to check them all.
Okay, that polynomial was pretty tame, right? But what happens when things get a little trickier? What about functions with trigonometry or square roots? Well, the beauty of this method is that it doesn't care. The 3 steps work just as well no matter how complicated the function looks. The process never changes.
So let's prove it. Let's tackle a trig function. We're going to find the extrema for this guy on the interval from 0 to pi over 2. And remember, the game plan is exactly the same. Find the derivative, find the critical points, and test all the candidates.
Now, we'll skip the nitty-gritty of the derivative work for this one, but trust me, when you do it, you find a critical point at pi over 6. So our candidate list is the endpoint 0, the endpoint pi over 2, and our critical point pi over 6. We plug them all in, and what do you know? The max value, about 2.59, happens at that critical point, and the minimum value, 0, happens at an endpoint. See? The method holds up perfectly.
Okay, next up, I want to show you an example that trips up so many people. It's a function with a square root. We're looking for the extrema on the interval from 0 to 4. And the key here is to not panic. We're just going to stick to our 3-step method.
So we go through the differentiation rules, and this is the derivative we get. And notice what it looks like. It's a fraction. We've got x minus 1 on top and the square root of x on the bottom. This fractional form is a massive clue. It's telling us something really important.
Okay, let's go back to step 1 for a second. What did it say? Find where the derivative is 0 times or where it's undefined. Now, almost everyone remembers the equals 0 part. That's easy. You just set the numerator to 0. But what about the other part? Where is this derivative undefined? This is the trap. This is the part everybody forgets. And here's the key. A fraction is undefined when its denominator is 0, right? So where is the square root of x equal to 0? At x equals 0. So we actually have 2 critical points to check. We've got x equals 1 because that makes the derivative 0, and we have x equals 0 because that makes the derivative undefined. You absolutely have to check for both. So let's look at our final list of candidates. We've got x equals 0, which is interesting because it's both an endpoint and a critical point. Then we have x equals 1, our other critical point, and finally x equals 4, the other endpoint. We plug all 3 into our original function, and we get back 3 values, 0, -2, and +2. A quick comparison tells us our absolute max is 2, and our absolute min is -2. Done.
So when all is said and done, what's the big takeaway here? It's that this 3-step method is your map. It is the most reliable way to find the absolute highest and lowest points on any function's trail, as long as it's on a closed interval. Let's just nail this down one last time. Step 1, find your critical points. That's where the derivative is 0 or undefined. Don't forget undefined. Step 2, make your list of candidates. That's all your critical points plus your 2 endpoints. Step 3, plug them all into the original function and just compare the values. The biggest is your max, the smallest is your min. That's it. That is the foolproof map to every absolute max and min you'll ever need to find. And that leaves us with one final thought. We've just learned a super powerful tool for finding the absolute peak on a graph. So where else does this kind of thing matter? I mean, what else in science or business or engineering needs to be systematically maximized or minimized? Think about maximizing a company's profit, or minimizing the cost of materials for a project, or even figuring out the most fuel-efficient path for a rocket. This hunt for extrema, it's not just in a textbook. It is literally everywhere.